Um, we'll start here. So let me go ahead and just explain what the code's doing, and then we can go into what each of the operators are going to do. So I basically have in main, I just have two different unsigned character values. I just set one to 179 and the other to 240. I did the 240 on purpose so that there's four ones in the front and four zeros and on the right side. And then I picked a 179 just so there was a more or less even distributions of ones and zeros. So that was kind of arbitrary. Um, but the reason that I pick these numbers and I care about these ones and zeros is because we're going to do bitwise operations on these, which involve actually manipulating the individual bits of these variables, right? And that sounds kind of weird, but it's not too bad because it's just built into C++ to actually manipulate values. Okay, so this function basically is going to be used by each input that I give it, each bitwise operator. So let's go through the parameters real quick, just so this makes sense. So the first parameter into this function is just going to be like the name of it. So or, and, XOR, negation, stuff like that. And that just simply prints that out. So that's not too bad. The other two variables are variable one and variable two, which I never end up changing these. So theoretically, I could have just left them inside of the function itself and not had to pass those in. But if I ever change these, it gives me the ability to do that. So these are going to be passed in here. And what I'm doing on lines 9 through 11, you won't have to worry about in this lab. This is basically only done so I can see the individual bits, so the ones and zeros. So this sets it as a bit set object, and I'm able to print it out as a bunch of ones and zeros rather than actually manually converting these things, right? So that's the only thing going on 9 through 11. And then the last one, last parameter that is going to be the result. So this should be character here. I don't know how that actually worked. That should just be unsigned character. And that's the actual result. So that's what the actual or value in this case is what I'm giving and passing into the result. Others will be ands and XOR. Yeah, question.
Yeah, that bit set object that you created, is that or is that something that you designed, or is that part of the standard library?
Yeah, good question. That's just another include you can have. Yeah, good question. So I definitely did not design that.
Okay,
yeah,
thank you.
great question. Yep. And like I said, as far as I know, you're not going to need this for your lab. So you don't really have to worry about that. That's mainly to prove some concepts here and make that more readable. So then we get the result and we do the same thing to the result. I just change it to a bunch of ones and zeros, and then I just basically print that information out. So looks like a lot of stuff, but there's really not much to it that's actually going on. So we can take a look at this first bitwise operator we're going to do, which is going to be the OR. So what OR is going to do is just basically look at each individual bit. And if there is a one, it's going to return one. So a one or a zero will always return one. A zero or zero will return zero. And then a one or a one will return one. You can think of ones as true and zeros as false. So you guys know in if statements, if you have like if true or false, you always know it's going to go into that if statement, right? Because at least one of those things is true. So that's kind of the behavior we're going to see here. And so hopefully this output makes sense. So this is the OR operator. I'll be printing out a lot of these, so it's helpful to have some kind of separator and a name for it. And let me go ahead and zoom in for you guys, just because we're looking at some small output here. Cool. So with these ORs right here, you can see that basically if you kind of look at these things as columns, you can see that anything that had at least one in it is going to turn out to be a one, right? So the very rightmost column, which we would call the least significant bit in this case, would be 1 and 0, which is going to turn out to be a 1. Again, a 1 and 0 is a 1. You get two zeros here on both. That's always going to be 0. And then two ones are going to be 1. So that's kind of the behavior of the OR bitwise functionality. Again, I'm printing out all these ones and zeros just so you can understand the bitwise more. But in reality, as far as the system is concerned, and our output is when you OR 179 with 240, you get a value of 243. So when we talk about actual like integer values, that's kind of the values we'd get. Some of you that might be familiar with signedness, so unsigned versus signed. Most of the time, signedness is done with the most significant bit. They basically replace that with the signed bit. So if it's a one, it's going to be a negative value. If it's a zero, it's not. These are unsigned characters, so they aren't going to have that behavior. So we can actually leave that most significant bit. That can either be a one or a zero, and it won't affect the signedness. That's also why when you change something to a unsigned variable, you're actually able to get a larger range, right? So if we have an unsigned character, we can get 0 to 255 versus a signed character where we only have negative 127 to 127. So, and I can talk about that a little bit later if you guys have questions on that. That's not super important for the lab specifically. So the next thing we can take a look at is and. So with and, we get kind of the opposite behavior of an or. So if it has just a zero, or if it has at least one zero, it's going to be zero. So you can think of this again as an if statement, like if true and false. I think you guys understand that that will always be false. It will never go into that if statement because one of those things is false. Same concept here. So we have a one, we have a zero. That's going to return zero because at least one of these things was zero. Same concept for this row. Obviously, both of these are zeros, so we're going to get zero. The only time we get ones are when both things that we're anding are ones, right? When both its bits that we're anding are ones, that's the only time we're going to get a one. So the or and are very similar to what you guys are used to with just like basic, if statements and control flow, right? Where you have ands and ors. Something that I didn't mention is the actual symbol for the operators. So you can see that this is just a single pipe as opposed to double. The double would be used in like control flow stuff, right? With like if statements. This is just going to take a singular pipe when dealing with bitwise operators. Same thing for that. And it's an ampersand, and you have two of them if it's going to be for if statements, but only one when dealing with actual bitwise operators. So I should probably say Booleans as opposed to if statements. It's just most of the time you're using Booleans and if statements, but that's kind of the concept there. So the next one's a little bit weird. I guess I'd stop. Any questions up till now? All right, cool. So the next one, a little bit strange. It's XOR. And if we go ahead and make this one, basically this one will return a one if the two bits are opposite of each other. So if we have a one and a zero, we're going to get a one. One and a zero, we're going to get a one. But anytime we have two zeros or two ones, we actually end up with a zero. So that's kind of the behavior of the XOR. It's a little bit strange. It might seem a little bit unintuitive, but there are cases in which this will be useful to use. And I should mention that if you're like computer engineering, so not computer science through engineering, but like straight up computer engineering, a lot of this stuff will you guys will use a lot more. So when you go to like digital logic, microprocessor stuff like that, you'll be using this a lot more intimately than you will in just other software engineering disciplines. So if you don't get used to it now, you'll get a lot more used to it later on. Or you might already be super familiar based on the courses you've taken. So negation. So we'll do two of these at a time. This one kind of makes, I think, the most sense. You're basically just flipping the bits. So we're doing negation on variable one. So you can compare this top one to this. I'm not doing anything with the variable two here. So you can see all the ones here are flipped to zeros down here, and all the zeros here have flipped to ones here. So that's the negation symbol. That's just I think tilde is what they call that, in front of the variable. It's the same symbol as like what you'd use on your destructor. And I forgot to mention that the XOR is the caret symbol. So that's above the 6 on your keyboard. That's what's used for that. And then the negation on variable two, you can see this one's a little bit easier to see, that basically all these ones flip to zeros and all these zeros flip to ones. So these are a little bit more, not complicated, but something you probably haven't seen before. And this is what you'll actually be using in the lab are these shifting. So if you haven't paid attention yet, this is probably where you want to tune in. So if I go ahead and look at this shift left 4, basically this syntax is telling the variable 1 to shift left 4 bits. So if we take a look at this right here and then compare it here, you can see these 4 bits have shifted 4 spaces over to this side. And basically the right hand side is padded with zeros. So you can kind of picture it as a bunch of zeros being pushed in from the right 4 times, and it's going to push everything to the left, right? And if I was to change this to just a 2, let's say, you would get the same behavior, except this portion would only shift to the left twice. So we still have these other 2 ones out here. So basically this chunk is matching this chunk right here, and it's shifted to the left twice, again padding with 2 zeros. And we can see that same behavior, and this one might be a little bit more clear by shifting left this one. So basically all 4 of these most significant bits over here were completely pushed off of this value, right? Because we shifted everything to the left 4 spaces, so all those ones basically got like dumped off the cliff. Basically, they were all pushed to the left. I'll go ahead and comment these shift rights in. So same concept here, except we're going the other way, right? We're shifting stuff to the right, and this should be 4 for right now. So this is shift right 4 for variable 1. So you can see these 4 match up with these 4 because it was shifted the other way this time, again leading with zeros. And then this one I think is the most clear, where all 4 of these were shifted 4 spaces this way. Weirdly enough, this is actually kind of the same thing as the negation. It's kind of the same as flipping. That's more of just a coincidence. So if I change this to a, I'm going to do a 6. Yeah, that's fine. You can see that there's only 2 of them left because it was shifted 6 spaces. So all 6 of these spaces were pushed off, and only these 2 bits remain for the shifting. So any questions on the negation or any of the shifts?
Yeah. So if you do a shift, say with whatever, and data gets pushed off, is that data lost? Or if you undo the shift by shifting, so if you shifted right, if you shift back left, do you regain that data, or is it just completely gone?
Good question. So we can take a look at this, but I'm pretty sure it's just going to be gone. I think if you shift right, like if you shift back right, it's basically going to just pad it with zeros. So if we take a look, let's see how I want to do this. Can do, we'll just do this out here. So if we do variable 1, 4, and let's basically update this variable, and I think that's where the answer is going to maybe depend. So if we're actually updating this variable with this shift, and let's do variable 2 because I think it's a little bit easier to see. And then we're going to have to do the bitwise thing again, which is fine. And let's see here, variable 1 and 1. Okay, and then let's comment these out for right now. Okay, so assuming I've done this correctly, and I didn't. So this is a character, so we just need to assign that to an int. Okay, so this is just the normal variable, and this is the wrong variable because this should be 2 and 2. So let's try this one more time. Okay, so that's a bunch of zeros, which makes sense. Or does it? We want to shift right. Sorry about this. Okay, so this is what we had before. So you guys know that it was here, and then I'm shifting it right, and then it's here. So now the question is if this is not a good example because those are going to be zeros anyways. Okay, let's try this again.
You could just shift it like 6, and it would have the same effect.
Right. Good point. Okay, so let's do that. And prove that. So, okay. And then if we shifted this back, which my guess is I think it's going to be lost. So we shift that back 2. And then do the same thing here and make this another. And this is going to yell at me. We're going to make just that a 3 for right now. Okay. Yeah, so you basically just lose that data, which is what I was expecting, but I just wanted to make sure I was right on that. So when you shift it back, it's just going to get padded. So when you shift it and those things, quote unquote, like fall off the cliff, like they're just being pushed off, those are going to be lost forever. So
okay, thank you.
Yeah, no problem. Good. That was a good question. I'll definitely leave that up there for my other labs tomorrow. Okay, yeah. Any other questions about any of this? All right, cool. So we can take a look at what lab 8 is going to be. So in lab 8, you're going to, in general, just going to get a bunch of files that are going to be like the colors txt, and those are basically going to look like this. So I think this is the first one. So you're going to get a name, and then you're going to get just some integer number. Okay. In that integer number, I'll scroll back up to this in a second, but in that integer number, it is a 32-bit integer, right? And basically, you're going to go into this integer and you're going to break it up and find each individual pixel value. So similar to Project 2 in the sense that there are pixels. This time it's going to be red, green, blue instead of blue, green, red. But all of that data for these blue, green, and reds are all shoved into one integer. Okay. So that means you're going to have to be responsible for getting individual chunks of 8 bits out of this 32-bit integer. Okay. And you're basically going to do that by the shifting, right? So you're going to be able to shift over this integer and basically grab the different bits that you need from it. So for the blue byte, you don't really need to do that because it's already at the 0th index. But for the green byte and the red byte, you are going to have to shift over to actually grab that value. In these documents, I think he makes what I went over as well just a little bit more clear. So you can kind of almost view this, especially for this lab, as like a window, right? Because it's 32 bits. And if you shift left by 1 and update the value, that's actually going to just shift left 1, and then these are the 8 bits that you're looking at, the actual like window, right? Where value is just going to be a unsigned character or like a UN8 if you're familiar with that. Yeah. So I think the best is just to make them an unsigned character because that will give you the range of 0 to 255. Similar to Project 2, that's what you need these to be, right? That's 0 to 255 basically represents an 8-bit chunk of data, which is what RGB values are typically written in. So once you do the shifting, and I'll leave you guys to read all this because it's for me to explain it, I basically just be reading the document. And that's kind of the high level concept here. And then you can also AND it with 255, the result that is of each of the blue, green, and red values. And that will just guarantee that you're getting all the ones and zeros from the correct way. So you can see here that basically all these ANDs will provide you with ones and zeros. So the second part of this, once you have the red, green, and blue value, is you're going to actually convert these to a hexadecimal conversion. There's no real functions built in for you to do this, or there might be, but you're going to have to do it in kind of a manual way, where you need to actually check what each of the values are and then convert those to the hexadecimal value. The hexadecimal value is going to be 6 different individual digits. So for those who aren't familiar with hex, it's base 16. So you basically have values from 0 to 15, which are 16 discrete digits, right? And then for us to be able to get 0 through 16 without using 2 digits to represent like only 1 digit, you actually have to go into the alphabet, right? So 0 through 9 is how you represent 0 through 9. And then A is 10, B is 11, C, D, and E, and then F is 15. Okay, so that's how you're basically gonna represent these. And this is probably the clearest way to show this. So this is decimal or base 10. Hexadecimal is going to be base 16. So that's what you're looking at right here. I think something to make this a little bit more clear would be to show you this. So let's go ahead, pull that out. And okay, so basically what we're looking at right here is the RGB values, which you're going to pull these out from an integer, and then you're going to convert these three things into a hexadecimal value. Okay, so this 32 right here is actually referring to 50. 168 is referring to A8, and then this 52 right here is referring to this 82. So if I was to change this value here, this 50 to an 82, what you'll see is it's actually updates to be 52, A8 and 52. So each 2 digits in this hexadecimal value are representative of one of these RGB values. So 255 is FF, which is right here. So that's what that value becomes. 0 is just going to be 0, 0. And then you can see 1, 2, 3, 4, 5, 6. And then once you get a 7, 8, and then 9 would be 9. And then once you do 10, this will just turn out to be A, right? Because A is equal to 10 in decimal. And then 15 would be F, and then it's going to, whoops, that's not what I wanted. I wanted, what is that, A? 15 will be F, and then if I made this 16, I think it's going to be 1, 0, because that's basically it incrementing and adjusting the next digit to the left. So something that'll help is just like a decimal to hex converter. I think doing this color picker will be helpful because you'll actually be able to put these values in and see if you're getting the correct values out. And then something like this will also be helpful when you're converting from your decimal to hexadecimal. So 255 again will be FF. And you'll actually be able to see the binary value as well. And he goes over a lot of the math to make this happen. So that might sound kind of convoluted to make that work, but he goes over a lot of the math to make that happen. I believe you have a color class for this, so you'll basically just copy this. All your red, green, and blue values are going to be unsigned characters. I think he just defines that for you. I know these are getters, but that obviously means the private variable is going to be an unsigned character if that's what it's returning. You're going to end up storing your data that you're converting into a map. So I believe you are having the name of the character as a string. And then I think the value might be the hexadecimal value, but I could be wrong on that. But your basic output is going to look something like this, where if they search for a color and type in the name of the color, you're going to get the name of the color and then the hex value and the decimal values of the red, green, blue. So if I went over here and typed in that color, which was 0, 255, 255, you can see that's cyan, and that's what that color is. So yeah, let's see. And then for the search, this is basically just printing them all out. So I don't think this is actually a search. They just typed in 1 for show all colors. So it's similar to the states, right, where you can search for 1 or you can just show all of them. And it's kind of the same concept here. So any questions on this?
How do you make it so it's like a table, like the columns?
Right. So I think that will just be a bunch of manipulating through the C out. I think you can use, I want to say it's, let's see if I can make this happen.
I think we did this thing then, like the first lab ever.
Yeah, exactly. I don't think you're gonna need the set W stuff. I could be mistaken there, but I think there is and I might butcher this here, but I think it's like a T, which basically creates a tab. Yeah. So you can use this T character, and that will actually create a tab. It's similar to, if you're familiar with, you can also make a new line by doing like this
Yeah.
and in, you can do the same thing. Same concept except with a
Yeah.
T. So
But
this
thing is
is
like,
where
but if some like strings are longer than the others, and like the tabs would push stuff like everything wouldn't be in the same line, no. But I guess we could.
yeah, good point. Yeah, so you there might be the chance that you're using
Uh,
the set W. I'm not super sure though. You should be able to find that stuff like on like your lab one though. I think because I think that's where you used it. So, and I don't know if Zybooks has any information about that on like the exact table outline. So I know that probably didn't answer your question super well, but
no, no, no,
I
it was
think
good. Thank you.
okay. Yep. Any other questions?
Yeah, do we have to use that class structure? Can we like use a struct and do that? Or are these functions like called in a pre-written name?
I believe so. The actual functions will probably be called. So I imagine you're going to have somewhat of this layout. Because he's probably going to make a. Let me check Zybooks for the main. I don't know if he'd give this to you if you had a choice of not using it. Let me check
Okay.
what this looks like. Yeah, he makes a at least in the main, he actually already like he makes a map of your color um, object. So yeah, he includes color.h in the color CPP. So I think you'll have to end up using it.
Okay.
Yeah. I guess unless he lets you edit main, but obviously like doing that is going to mess up some of the tests possibly. So as far as I can tell. At least the output. Actually, looking at this, if he lets you edit main, I guess you could just, change all of it. But of course, doing that, you might mess up, like, how exactly the tests are going to be ran on it, and you might not get all the points. So, yeah, good question, though. Any other questions?
It's not about the lab specifically, but on Canvas, it says that it's due on the 18th. I just wanted to make sure that that was correct because this is kind of the first time that we've had 2 weeks for a lab.
Yeah, good question. So let me go ahead and take a look at that. I'm sure I'm just going to see the same due date as you, and I imagine that that's probably when it's due. I think this year got a little bit weird with the scheduling, just because there was no spring break. I think in semesters past, yeah, April 18th. Yep, yep. So you should be okay to turn it in then. Both Canvas says that, and I think let me see here. I don't know if Zybooks. Yeah, Zybooks doesn't even have a due date yet. I don't know if some of you can see this or not yet. I know that some of my students have already worked on it. For me, it's actually hidden on Zybooks. But yeah, I think it should be due the 18th. So, but I think just with no spring break, I think our due dates got a little bit weird. So, yeah, cool. And then I think I saw in the chat. I'm sorry I didn't open it earlier, but I think your question got answered. So, cool. Anything else? All right, sweet.